see questions in the chat, I may be, too busy to notice them. So feel free to interrupt and
sure.
Say,
Yeah.
Jonathan, there's a question about this or something.
Yeah. I'll moderate that, don't worry.
Thank you.
So. So, hello everyone. Good morning. And it's almost it is midnight for Jonathan. So, hello Jonathan. It's very nice to have you over. And so let me introduce Jonathan McDowell. Jonathan McDowell is an astrophysicist at the Harvard Smithsonian Center at Boston, and he works with the Chandra Xray Center. He another important thing that Jonathan is busy with is he's the author and the editor of Jonathan's Space Report, where he actually has an email distributed newsletter which actually documents satellite launches all over the world. So it would be a good idea to register for his newsletter. You get all the updated information about space launches all over the world. So Jonathan does that, and along with that, he's also very active with work with Chow, which is the software which is used for Chandra data analysis. And welcome, Jonathan. And
thank you, Priya. Yeah. Well, thank you. Hello, everybody. Good morning or good evening, depending on where you are in the world. I'm going to share my screen and tell you about doing science with Chandra, and in particular, doing science with the Chandra Science Archive. So this is a nice picture of Chandra. Chandra is a 5-ton space telescope that was launched all the way back in 1999. It's still orbiting the Earth, and it's still returning great data. Let me see. It is the highest spatial resolution X-ray telescope. There are other X-ray telescopes, notably the XMM Newton telescope from the European Space Agency, and of course AstroSat that ISRO operates. And one of the great things about X-ray astronomy compared to some other sub-branches of astronomy is that there's a lot of standardization in the software. So even though I'm going to talk about Chandra data, a lot of what I say carries over to XMM and AstroSat and NuStar and the other X-ray satellites. Chandra is operated by the Chandra X-ray Center, which, as Priya said, is in the Boston area in Cambridge, Mass. And our goal is to try and make it easy for people who aren't specialists in X-ray astronomy to get science done with Chandra. So I'm going to talk about what it can do, how to analyze its data, and I just want to mention the Chandra source catalog as well. So here's Chandra. It has X-ray mirrors at one end, cameras at the other. It's 10 meters long. And it's in this really high orbit. It goes out to 140,000 kilometers from the Earth. And so it takes about 2.5 days to orbit the Earth. And it has these two main cameras called ACIS, the Advanced CCD Imaging Spectrometer, and HRC, the High Resolution Camera. Mostly I'll talk about ACIS. The HRC is sort of a backup camera that's used for certain kinds of science, but sort of like 90% of the observations are with ACIS. So there's a little more detail. ACIS has 10 chips, each of which is a megapixel. So it's a 10 megapixel camera, which for 2021 is not that impressive, but for 1999 was really good, especially as they're X-ray 10 megapixels. So what's special about Chandra is that it has such high spatial resolution. On axis, in the middle of the field of view, it's less than an arc second. And each chip has an 8 arc minute field of view. And you don't just get pictures, it's like an integral field spectrograph. You get a spectrum, a pretty low resolution spectrum, but still a spectrum in every pixel. When we cover an energy range that's, depending on where you cut off the boundaries, is about a half a kilo electron volt to 7 kilo electron volts. So in X-ray astronomy, we use KeV instead of wavelength in angstroms or frequency in gigahertz that you might do if you're an optical or radio astronomer. So 1 keV is about 12 angstroms. So about 100 times, several hundred times shorter wavelengths than in the optical. So as I say, there's the HRC camera. There are also 2 transmission gratings that we can put in the optical path to disperse light. So instead of getting a spectrum, low resolution spectrum in each pixel, you get a dispersed spectrum across the camera that's very high resolution. So for bright sources, when you look at the bright source, you might want to do that and then really see something more like a classical optical astronomy spectrum with visible lines and so forth. And so Chandra can do a range of different kinds of science. We do deep searches for measuring the brightness and the position of faint point sources. Because we have such high spatial resolution, we also have very low background. And so we can see really faint things. There's a couple modes. I won't go into it, ACIS, ACIS-I, or ACIS-S. They're just which chips you choose to use. Used to matter a lot more, but really it doesn't matter so much these days. So the other thing we can do is we can do this integral field spectroscopy of bright sources like supernova remnants, and so get a spatial map that's also a spectral map. And each pixel has a spectral resolution about 50 to 100. That means the fractional spectral resolution delta E over E is about 1 over 100. And as I say, we have very low background, so we can make very pretty pictures. And then the high resolution spectroscopy uses the gratings, and that's about 10 times higher spectral resolution, but you only see the thing in the middle of the field. So as I said, I'm gonna talk about the ACIS imager because that's the majority of the results, and also it's the one I understand the best. So here's a classic Chandra picture. It's actually a 10-day long exposure of the supernova remnant Cassiopeia A. And what we've done here is we've taken the X-rays over the energy range of half to 10 kilo electron volts or so, and we split it up in colors by doing a continuum image and then isolating X-rays with energies around a couple of spectral lines, the silicon line and the iron line in red and blue respectively. And so what this is showing you in green is the shock wave of the exploding star as it travels through the interstellar medium. And then the clumpy stuff inside going a little slower than the shock wave are the freshly baked elements from the supernova. And so there's probably a couple solar masses of iron in these blue blotches here. So we can really see how the classic, if you've done the classic astronomy textbook with supernovae and you've seen the onion diagram with the different elements in nice, beautifully spherically symmetric shells around the center of the star, we see that actually it's not quite, it's a little messier than that in real life. We can also look far out into the universe. This is a very deep exposure. It's probably a couple of weeks accumulated exposure time to look at a boring empty piece of sky, a survey field, to see what we can find. And what we find is almost every dot in this image is a quasar. It's an active galactic nucleus, matter falling onto a supermassive black hole, getting really hot and radiating in X-rays. And one of the great things about X-ray astronomy is it's a great way to find quasars because most of what you see is quasars. So you'll also notice in this image that the things towards the edge of the picture look fuzzier than the things in the middle, big blobs instead of sharp points. And that's a feature. Oh dear. I apologize that my computer is making a "I'm about to die" whining sound, so please ignore it as best you can. So the field of view here, as I say, is the sharpness of Chandra's vision degrades towards the edge of the field. So in the central few arc minutes, it's sub-arc second, but towards the edges, it's more like 10 arc seconds or worse. Another nice thing we can look at are quasars with jets. One of the things that Chandra discovered shortly after it went up was that X-ray jets from quasars are much more common than we had expected. At the bottom right here, this was the first focus image that Chandra took. We thought we'd point at a point source and make sure that the mirror was okay, so that we would check that we didn't have another Hubble disaster on our hands. And we got this image back, and initially we were freaked out because we saw this other feature, and we were worried that something was horribly wrong with the telescope. But then we remembered that there was a radio jet at exactly this angle. And so it turned out, in fact, that our first "let's test the focus" image actually made a major scientific discovery. And so we have better images here, these very long, very collimated jets that we think are electron-positron jets going at 99 point something the speed of light, relativistic jets that are glowing because cosmic microwave background photons are bouncing off the relativistic particles in the jet. And that's making the X-rays. Nearer to home, this is the galaxy M33, and you see here we've done a mosaic. So there's an observation here with 4 chips, and there's another observation that we've overlaid that has 4 in a square and 2 off axis. And so there's different configurations of the ACES camera that you can use to get these different shapes. And what you see in this nearby galaxy, see a lot of background. You see some of the chips. There are 2 chips that have higher background than the others, but they have good properties in other respects. And you'll see a lot of point sources, including this bright one in the middle, which is a very luminous X-ray binary. And so most of what you see in this picture in terms of sources is X-ray binaries or supernova remnants in the galaxy M33, although there are a couple of fuzzy splodges here and here, which are actually hot gas in star formation regions, that it's 1,000,000 degrees. And so with X-ray astronomy, you see 1,000,000 degree gas, as well as extreme conditions as matter is falling into black holes and the hot 1,000,000 degree gas from supernova remnants. This is another observation I made of 2 galaxies that merged. This is the famous object ARC-220, the most luminous object in the neighborhood. And by the neighborhood, I mean the closest 250 million light years. It's about 10 to the power 12 times the luminosity of the sun. So a 1,000 billion times the solar luminosity. Most of it is in the infrared, but when you look in the X-ray, you see this hot gas. This is an X-ray color picture that I've made by dividing the Chandra data into 3 energy ranges, like 0.5 to 1 kilo electron volts, 1 to 2, and 2 to 7, coloring them red, green, and blue, and then adaptively smoothing them to make a pretty picture. And you see in the low energy X-rays, the red, you see on this left-hand image of the merging galaxy, hot gas that's undergone shocks from the collision of the galaxies. Right in the middle, then there's a yellow area that's where there's intense star formation, a starburst going on. And right in the middle, there's a slight hint of blue, which is where the supermassive black hole is hiding. And the supermassive black holes tend to have much higher energy X-rays than the diffuse gas. And so when you look in the high energies, you tend to see point sources that are often quasars. But there's also one other source out here that's a ultraluminous X-ray binary just sitting out in the outskirts of this galaxy. And it turns out if you make a bigger field, there's this big red blobby thing here that's actually hot gas in a cluster of galaxies twice as far away, so 500 million light years away, just happens to be in the same direction on the sky. And it's got galaxies embedded in it. But most of the mass, we now know in clusters of galaxies, most of the baryonic mass, most of the stuff that isn't dark matter, is actually not the visible galaxies. Even so, it's these million-degree gas in the cluster. So that's some of the kinds of objects that we see with Chandra. So now I want to talk about how we actually do the data analysis project. So there's various kinds of processing that we do to X-ray data that's pretty similar to what you do in other fields of astronomy. The standard calibration and reprocessing of the data, spatial analysis to make a ray trace to model the point spread function, which we'll talk about more, and compare it with the counts image, ways of modeling the background of the detector so that you can subtract it off and get the true source emission. And a lot of what we do is spectral analysis as well. So here's a spectrum as a function of energy. Actually, that's the sensitivity of Chandra as a function of energy. We want to understand what, take that signature out and find the true spectrum of the source. But sometimes you don't have to go to all that trouble of doing the data analysis. The first thing you want to do if you have a science project is check if the data is already processed in our Chandra source catalog. So this catalog went through the entire public Chandra archive up to 2014. We automatically processed it in a consistent way and found over 300,000 X-ray sources with accurate positions and with brightnesses in 3 energy bands. And so you can go to the Chandra Source Catalog website and search for a particular region of the sky to see if we've seen it. The bad news is we've only done about 1% of the sky in the 20-something years we've been observing. So your object might not be in our catalog. The good news is we've done the most interesting 1% of the sky. So there's not a bad chance if you have an interesting object that it might be in a Chandra observation. And so you can, if you have, for example, a simple question that you want to answer, like, I know the infrared brightness of my source, but I just want to know what the X-ray brightness is, or if it's been detected in X-ray, this is a good way to go about it. And if you're looking at stars or nearby galaxies that are bright sources, and you want to see the high resolution spectrum, we have the transmission grading catalog TGCAT that's run by the folks at MIT up the street from me, and tgcat.mit.edu, and that has the fully processed spectra from the gradings that I mentioned earlier. But there's a lot of data that isn't in the catalog, everything since 2014, and you may need to analyze the data yourself, or even at some stage in your careers, propose to Chandra and get shiny new data from the telescope. And so then you'll need to actually do some data analysis. In X-rays, we have a bunch of data analysis software packages that are mostly specific to different missions. For example, the SAS for the European mission. There's HeSoft, which does all the Goddard, NASA Goddard missions, but and I also believe it has stuff for Astrosat. And then there's Chow, which is for Chandra. That's the package that I'm involved in developing. And the good news, I said, is that in the 1990s, all the X-ray astronomers got together and agreed on standard file formats. And so all the data for all the missions in X-ray is pretty similar. And often you can use the same software to analyze data from the different missions. So I'm going to talk about Chow. Here's the Chow homepage, and it's on the cxc.harvard.edu website. And this software it's free, it's open source. It runs on either Linux or Mac machines. If you install it, it's very easy to install. You can do it with Conda if you're a Python fan, or you can do it with our Chow install script that just installs it on its own. Hello? Yep. Sorry, I thought I heard a question. And it takes about 9 gigs on your disk, most of which is calibration data. And the main way that we use Chow is as command line Unix tools working on FITS files. So hopefully you've come across FITS files already in some of the previous lectures, the standard astronomy image format, but it also supports table formats that are mostly what we use in X-ray astronomy. And there's lots of cookbook scripts and threads on our website to help you do particular kinds of data analysis. And there's even workbooks that give you example analysis to do. And so hopefully people will remind me to give you a pointer to that at the end. So I want to talk a little bit very abstractly about how we do data analysis in astronomy in general. Because I think we don't often talk about that, and it's helpful to sort of take a step back and look at the theory for just a minute. And so the problem we have as astronomers is that we have photons coming in at us from all directions as a function of position on the sky, of time, and of photon energy. Or you may be more used to thinking of wavelength or frequency instead of energy, but they're interchangeable, of course, for a photon. But what we measure is not this S, this field of income, is N, some signal from our instrument, actually from our data pipeline. So we take the sky and we feed it through a combination of a telescope, an instrument, and a software pipeline. And we get out data files that give us a signal that also varies in space, time, and energy, but they're not the real space, time, and energy. They're instrumental proxies for it. Image pixels, detector time tags, and instrumental wavelength or instrumental energy. And the process of observation takes the incoming signal, multiplies it by a sensitivity, which is going to be a bigger factor the bigger your telescope is, but also will vary across your camera depending on the quantum efficiency of the pixels, of how much gunk there is on the mirror. So some kind of calibrated sensitivity. And then, this is the nasty part, it smears it from the true coordinates to observed coordinates. And so what you end up with is data set where you think you have a picture of the sky, but in fact it's smeared, it's convolved with the response of the telescope. And our game is that we know N, we've measured N, and we have to calibrate A and R, and then we have to try and invert this integral to get S. And in optical astronomy, often this R, we just assume it's diagonal. It's a simple a diagonal matrix, in which case you can just cancel out this integral and S is N over A. But in X-ray astronomy, the resolution isn't good enough to do that a lot of the time, and we have to work a little harder. So what is this R, this smearing function? The spatial part of it is called the point spread function. The point spread function is I have a point-like star, I shine it at the telescope, and it gets smeared out on the detector to a blobby thing, depending on how good my mirror is. And this function is, what's nice about it is it's linear in the sense that if instead of looking at a point-like star, you look at an extended, like a galaxy, a pretty object, the response of the telescope to that is just the sum of lots of little point spread functions weighted with how bright the galaxy is at every point. Then the other critical thing is what's called the line spread function, where suppose you shine, this is the x-axis is photon energy here. Suppose you shine photons that are all 2.65 kiloelectron volts, a perfectly narrow line at your telescope. What you'd like in an ideal detector is that it would just spit that line back out. Sadly, what you actually get is a smeared line where if the input photon is 2.65, there's some probability that what you actually measure in the camera is 2.4 or even sometimes 1.5. And so when you measure the energy of a photon in the detector, you measure this instrumental energy, you get, oh, my photon is 1.5. No, it might really be 2.6 or something like that. And so the function that probabilistically smears your line out into different energies is, in optical astronomy, the line spread function, but in X-ray, because we have to do things differently, it's called the RMF, the redistribution matrix function. You don't have to remember that, you have to remember RMF, which is the name of the file, the calibration file that describes this smearing. Then the final thing you need is that multiplication factor of how sensitive the telescope is. It's called the effective area. It's traditionally measured in square centimeters. So if you had a perfect telescope, this would be a horizontal line independent of energy on the x-axis that would be equal to the geometric area of the telescope. Obviously, the bigger telescope you have, the more photons you catch, the more area you have, the more collecting area you have, the more photons you see. But at any given part of the detector, that geometric area is multiplied by a fudge factor, depending on how sensitive the mirror and the camera combination are. And it has nasty features in, like this jump here, that are due to atomic physics properties of the pixels or of the mirror. In this case, it's the mirror. So we're looking at, in X-rays, at atomic transitions and transmissivity of various atoms as a function of energy. But our telescope mirror is made of atoms too. And so we see spectral features that are due to the telescope mirror, as well as spectral features that are due to the astrophysics. And so we have to take these out with this calibration file, which is the effective area, also called the ARF, the ancillary response file. The thing you need to remember is ARF, ARF, that's the file name that this calibration is in. And so all I've said so far is sort of, it's basically true, not just of X-ray astronomy, but of optical astronomy as well. But there are some differences in X-ray astronomy. And so I've listed 5 big problems here, which are problems that you haven't come across in other kinds of astronomy. Problem 1 is that X-ray sources tend to be really faint. And so you might only have 10 photons in your source instead of billions that you might have in an optical picture. And so we have to be very careful about the statistics. You have to become a little bit of an expert on statistics to get the right error bars on your measurements. Small number statistics, typically the Poisson distribution tells you what your error is going to be on a flux, for example. The second problem I already talked about a little is that that line spread function that smears the data in energy is not narrow. So in optical astronomy, again, you have an instrumental width for a spectrograph, but it's pretty small and you tend to ignore it. You can't ignore it in X-rays. And so that makes things very complicated, comparatively speaking. But you know, we know how to do it, and it's once you learn the tricks, it's fairly straightforward. The third problem is that the X-ray band is really broad. In your minds, probably you think of X-ray as just another thing in the same bucket as optical or near infrared or ultraviolet. But the Chandra band covers more than a decade. In fact, it covers a decade and a half of frequency space. And so that's actually equivalent to having a single telescope that looks all the way from the mid ultraviolet through the optical to the end of the near infrared. And so in fact, you know, you don't do that. You have 3 telescopes to do that normally, right? And so what that means is all of the calibrations are energy dependent because we're covering such a wide range of energy that the way the telescope responds at one end of the energy band isn't the same as the way it responds at the other end. And so you have to be much more explicit about the energy dependence of everything that you do. The fourth problem is the optics, which I showed you in that picture of the deep survey where the quasars got fuzzier toward the edge of the picture. So your point spread function is very good on axis, but it gets worse off axis. And so you can't use just a single point spread function for the telescope. You have to calculate a point spread function for your individual source that you're looking at, depending on where it is in the picture. The final problem we call dither, and it's both a problem and an advantage. Our telescope doesn't point rigidly like something like Hubble or a ground-based telescope. We're not staring at the source. We're actually moving the telescope back and forth during the observation, smearing the image across multiple pixels. And that's partly to average out the pixel responses. But then you ask, don't you get a blurry image? No, because we also have, one of our advantages is we have more data on every photon than a typical optical picture. We have the position of the photon, we have also the energy of the photon, and critically, we have the arrival time of every photon. So what we telemeter down is a list of photons. We say, we saw an X-ray at 3 p.m. in this pixel with this energy. And so the fact that with telescope is pointing at a different place at 3 p.m. and at 3:01 p.m. doesn't matter because we're also telemetering down where the telescope was pointing at each moment. And so you know where the photon landed on the detector, and you know where the telescope was pointing at that instant. And so you can figure out where that photon was on the sky and reconstruct the sharp image that you wanted. So it is actually a big advantage in X-ray astronomy that we have these extra parameters for every incoming X-ray. So I just want to illustrate some of these problems that I've talked about. Let's go to this plot. So this is a plot of a model spectrum. And the model spectrum is has a lot of lines in it and some spectral features. And this is not what you observe. This is what nature throws at the telescope, and the telescope blurs it, and you get this red line, which has much less information in it. The black data points here show a typical data spectrum that we're fitting this to. So you get data like this, and so the game is you can't invert that and guess what, and derive uniquely what this line spectrum is. What you have to do is have a physical model that predicts this spectrum as a function of, say, parameters like temperature and gas density, and then take that model spectrum and in software convolve it with the blurry vision of our telescope to see what would our telescope see, this red line, compare that with the data, and that's known as forward folding. And then what you do is you say, okay, it's a bit off, so then we'll change the temperature in our model a bit, predict a new red line, and see if that fits better. And that way you can fit physical parameters despite the fact that you can't invert and get a sharp spectrum like this one. So this is just showing how the point spread function varies off axis. So you go sharp near the middle of the picture, and as you go off axis, as you go toward the edge of the picture, it gets much bigger and you get a lot of complicated structure. So if you're analyzing a source that's way off in the edge of the picture, you really have to do a careful job on modeling the point spread function if you need the details. So in addition to these general features of astronomical data analysis, we also have a couple of tricky instrumental effects that you want to deal with. One is Pileup. So Pileup is the way we actually do this trick in X-ray astronomy. We have the CCD in space. It takes maybe a 3-second exposure, reads it out on board. Onboard computer finds the events, the photons in that 3-second exposure, adds them to the list that it's going to telemeter down. So we don't telemeter down the raw frames. We telemeter down which events, which photons we found in each frame. And then you take another frame, add it to the list, take another frame, add it to the list. And so suppose you say, okay, I have a photon in this frame that has an energy of 8 kiloelectron volts. And so this bottom left picture is what I'm talking about. It might be, but instead what might have happened is in the 3 seconds that you were exposing, you might have got 2 photons arriving in the same pixel if you were really unlucky or if the source is really bright. And those 2 photons are going to be detected on board as if they were 1 photon with the sum of the energies. So you got a 2 keV photon and a 6 keV photon, and they arrived in the same pixel in the same frame. And when that frame is analyzed, you think you've got 1 8 keV photon. And so what that does is it takes the true spectrum in red here and slumps it to the right to make the observed black spectrum with fewer total photons, but shifted toward higher energies. This is called pileup. The photons are piling up in a single pixel. And if you have a bright source, this is a problem and it's very difficult to back out. So the solution to that typically is don't look at really bright sources, look at faint sources where the number of pixels arriving, the number of photons arriving in any one pixel in 3 seconds is low enough that this effect is negligible. But sometimes you can't do that, and so there are ways of dealing with this problem. And here's another problem, which is that if you look at a bright source, you see these bright lines on either side that are not real, they're instrumental artifacts, and that's because the ACES camera doesn't have a shutter. So when you're reading out the CCD, you use fields to clock the charge, to move the collected electrons down to the readout row of the CCD. Photons are still coming in and being counted, but because you're moving everything down, they land in the wrong pixel, and they're analyzed as if they came at a different Y value, a different row in the CCD. And it's mainly a cosmetic problem. You can do something for the analysis of these, what we call readout streak photons, but you may also just want to cosmetically remove them. And just be aware that that's what they are, and it's not that this object has 2 perfectly collimated jets coming out of them. It's not a real astrophysics signature. So so that's sort of the theory of what we're trying to do, now I want to talk a little bit more about the details. As I said, our data are in FITS formats, binary tables, So tables with columns and rows, and we'll see that in a minute. And the tools are Unix command line tools. And one of the basic tools is one that just copies one file to another. Here in the middle here, DM copy. You say DM copy, input file name, output file name. Well, you know, that's kind of useless, right? Except that all of the chow tools accept as file names what we call virtual files, which is this weird syntax I have up here. I hope you can see this cursor, where I go, instead of the file name evt.fits, I say evt.fits square brackets energy equals 300 colon 1000 comma sky equals circle x center y center radius close square brackets. And what that says is, okay, rather than giving me the whole input file, just give me those rows of the input file. So each row of the input file is an X-ray. And it has columns called energy and sky, which give you the energy of the photon, the instrumental energy of the photon in electron volts, and the pixel position. Sky gives you the pixel positions, X and Y, of the photon. And so it said, give me only those rows where the energy is between 0.3 and 1 kilo electron volts, and the data's near my source within 20 pixels of 4096, 4096. And so that virtual file, the software treats as if it was an actual file. And you can make it an actual file with DM copy, but it's very useful not to have to clutter your disk with all of these temporary files. So this lets you make these sort of subset files on the fly, passed as input parameters to the tools. Another really important tool is DM list. That lets you list what's inside the file, see what's inside the file, not just the raw data, but also the structure of the file, what columns there are in the table, and things like that, what header keywords there are. There's a tool called ahelp, which says, I don't know what DM list does or how to use it. How do I do that? It's like the man page. If you're familiar with Unix, it's the online help for every tool. And the tools take parameters on the command line. plist shows you what the parameters for that tool are, so you don't have to remember them. You can just go, oh, what parameters does DM list take? Okay, I'll plist it and find out. There's also a couple special tools that I want to mention. There's a tool called Sherpa, which is a Python application that has an interactive interface for fitting models to data. And actually, it's useful beyond X-ray astronomy. It's a very good general purpose parameter fitting engine. And there's DS9. Some of you may have come across DS9 in other aspects of astronomy. That's used for displaying files. And it's got special capabilities for displaying X-ray data files. So just to emphasize, in optical astronomy, you're used to dealing with images. In radio interferometry, if you've done that, you've got a visibility array. But in X-ray astronomy, what we're dealing with is the event list. This table where every row of the table is an X-ray, and every column of the table is some property of that X-ray, like its energy or its position. And our software makes it easy to make a picture from this event list. So if you give the event list to DS9, it'll just display it as a picture. And so it's easy to forget that you've lost information by doing that. You've taken a two-dimensional projection of this four-dimensional data set of X, Y, time, and energy. So I just want to show you for a second the full horror of what's inside the event list. In this particular event list, DM list, blah, blah, calls, it has 15 columns, various measures of the time, of the position of the photon, of the energy of the photon. And if you list the raw data, so you can look at this. You can actually investigate, if you really want to get into the nitty gritty, you can see the numbers for each individual photon, what time it arrived, which chip it hit, what sky position it was at, what energy it has. Normally, you don't have to go to that level, but it's important for me to tell you that you can do that when you need to. So that's what the raw X-ray data looks like. And just to sort of beat this a little more, here is one particular X-ray image. I actually showed you the merging galaxy earlier. This is sort of the raw data, and I've sliced it into different energy range, just using commands like this one, dm copy, energy equals, giving it an energy range, and using a bin command to make an image binned by a factor of 4 to have coarser pixels of a subset of X and Y. And so that makes these images, you just change the energy to get different ones. So at the lowest energies, 0 to 0.5 keV, there's a lot of noise due to the soft X-ray background, which is an astrophysical background. At the highest energies, above 10 keV, there's also a lot of noise due to cosmic rays and Earth magnetosphere particles going through the telescope and screwing up the detector. And so you really, one of the first things you want to do is slice off these low and high energies, because you're not going to get a lot of useful data there. And so between 0.5 keV and about 7 keV, you actually get signal. And you can see here in the different cuts that the fuzzy stuff is most visible at the lower energies. And as you go higher in energies, you lose that fuzzy stuff, the diffuse X-ray gas at 1 million degrees or so, and you get just the point source where the supermassive black hole is, that's has an effective equivalent temperature of maybe more like 10 million degrees. So the raw data, when we get it down from the spacecraft, also looks kind of like this. It has bad columns, boundaries in the instrument, hot pixels that are bogus, and you can barely see the source here. And this is called the level 1 event list. It's one of the files that you get given, the raw file. But we also are nice to you, and we run a filter on this to give you the level 2 file. So this is a level 2 file with also an energy filter applied to get rid of those end energy ranges that are not very useful. And now you can see much more clearly many little X-ray sources in the picture. And so normally you'll start off with the EVT2, the event 2, level 2 event list, which is the properly calibrated and cleaned event list. When you get to expert level, you'll sometimes go back to the level 1 and filter it a slightly different way to get your own level 2 list with your own data selections. But you don't have to do that too often. The other important file in the data is called the aspect solution. The aspect solution is a table of where was Chandra looking every 2 seconds of the observation. And so it gives the right ascension and declination of the optical axis of the telescope and a time tag, and also the rotation, what we call the roll angle of the spacecraft, so that you can figure out which way north is. And this file is the other main file that you need to do the data analysis, because this connects where you are on the sky as a function of time to where you are on the chip. And so when you have to apply calibrations that give you the sensitivity of particular pixels, you need to do that in the chip space. When you want to look at the astrophysics, you have to be in the sky space. So here is in the sky space a zoom in on a particular observation. It's a bit messy, it's not very cleaned. And you can see there's a bright source here right near the boundaries between the chips. You see these gaps here that are gaps between 4 chips. And you also see a readout streak on this source. Okay, that's nice. But what does the data really look like? Because this image is actually made from the sky coordinates, which are calculated in software. This is not the raw chip data that is read down from the spacecraft. That looks like this. And what you've seen is that our nice sharp point source has become a big fat square with missing rows in it, because the spacecraft, remember I said the spacecraft was not rigid but moving. It moves back and forth, And as it was doing so, this source was dithered on and off the chip into the chip gaps. And so being able to look with the software in the chip coordinate space is very useful because you can spot problems like this. And otherwise you might think, oh, if I do a light curve of the source, I have this weird 11-minute variability in the source. I've discovered something. No, you haven't discovered something, or what you've discovered is that the period of the spacecraft dither back and forth is 11 minutes, and every 11 minutes the source is being put onto the chip gap. So you have to be there. This is just to say you have to understand a little bit about how the instrument works in order not to get caught by spurious discoveries. You can also make what's called an exposure map, which shows the sensitivity of the field of view in a particular energy range. And what you see here is the chip gaps. And you notice the chip gaps are not perfectly black because, again, there is some time in which any given part of the sky is not on the chip gap because you're dithering back and forth. You also see the bad columns, and you see this circular structure, which is the mirror vignetting. That you have the most sensitivity on axis, and it gets a little worse as you go toward the edges. So what I want to remind you is that because we have this four-dimensional data set, you have to resist the temptation to throw away the two of the axes too quickly. But eventually you end up doing that. And so you can either throw away, so first you filter on the other axes. So you say, I want this energy range and this time range, and now throw those axes away and make an image of the photons that are left, or select filter on space, that's to say, give me just the photons near this source that I'm interested in, and throw away the time, and then make a histogram on the energy of the photons. So now you've made a spectrum, what we call a PHA file in X-rays. Or you can throw away the space and time information and make a light curve, so the space and energy information, and make a light curve by making a histogram of the data against time. And so now you have an extraction. Suppose you've made a spectrum now, the PHA file that's a number of photons as a function of energy. We're back to this equation I went to, a little simplified. So the software makes what's called a PHA file that gives you this, the number of photons as a function of instrumental energy. And it will also let you make an associated ARF and RMF for that particular source. The ARF is the sensitivity as a function of energy at that part of the detector on that day. And the RMF is the energy smearing between true and instrumental energy, the probability that if the real photon had an energy of 2 keV, that you actually measured it to be 1 keV. That's a matrix that is written in a thing called the RMF file. So these ARF and RMF files are made by the software. And then you go into the Sherpa software and pick the functional form of S of E that depends on some parameters. And then the software, once you've picked that S of E, the software can evaluate this integral and make its guess at what N of E should be that it can compare with the data and find the best fit parameters for S that best match this N of E. And that's spectral analysis in the X-ray. It's complicated, but we have all this software to help you do it, and threads to lead you through it. I'm not going to go through that. And so this Sherpa function, it says this general fitting program that can do that, but it can also do spatial fitting. So here's a nebula of some kind, and we're fitting a model to it and showing the residuals. And we can look in parameter space and get the contours of chi-squared to see the error bars on our parameters. And it comes with all kinds of fun algorithms. It has Monte Carlo Markov chain capability. So it has all the latest WYSIWYG spectra statistical tools. And You can get at the innards with Python, so it's very flexible. The other thing you'll need, and it's part of the standard software installation, is the CALDB, the calibration database. The thing that's really sweet about that is you download like several gigabytes of calibration data, but you never have to figure out which is which. The software looks in the header of your data and goes, okay, your observation was taken with this instrument mode on this day. And so the calibration files I need are these ones. And so it does all the hard work for you. So that's the good news. So what happens if you want to measure the brightness of a source? It's actually really complicated in X-ray astronomy. I'm sorry. The reason it's complicated is because of this energy smearing and the fact that we have such a broad energy band. We've made it easy for you with the source flux tool. You give it the event file and a position and an output file name, and it calculates for you various estimates of how bright the source is. But I want to show you here that the innards of it are really complicated. It calculates how big an extraction region you should use, what fraction of the source of the point source's light will be within that extraction region, what the energy bands are, and does a Bayesian analysis to get the count rates, corrects those count rates to fluxes using a spectral model, creates the RF and RMF so that you can properly do that calculation, and finally spits out the answer. So until very recently, until a few years ago, I should say, you had to do all this by hand, and now SourceFlux will do it for you. So I want to finish off in the last couple minutes, sorry, I'm running a little over, to take you through a quick analysis session that I did in the past few years. So I got an email saying, hey, Jonathan, your data's ready. We just observed it, but it's gone public now, so you can just download it using the download Chandra OBS ID tool within Chow, and you get directories. You get a directory called 18265, which is the observation number, subdirectories primary and secondary, which have the various files in. The first thing you always do is run the Chandra repro tool to reprocess it. That makes a new subdirectory repro that has all the files you're going to need from now on. In particular, evt2.fits, which is this event file, and pcad blah blah asol1.fits, which is the aspect solution file. So those are the two main ones you'll need, but you may need some of these others. And so then you can take this event file and do an energy filter on it to make a new file that only has the energy range that has good signal to noise. And you see this, I used 2 chips and not the full chip was read out, but you can sort of see there's some sources there. And here's my quasar that I was targeted on. This, by the way, is displaying it in the DS9 program. And you might be able to see there's a little slight fuzz here with the eye of faith. Let's see if there's something really there. So we slice the data into 3 energy ranges and then use C-Smooth, which is an adaptive smoothing tool, to make smooth versions of each image and then recombine them into a color JPEG, and you get this. So there's the quasar, but yes, indeed, there is something to the east of that quasar that turns out to be a cluster of galaxies. Now, you can't do much with this JPEG. It's the smoothing takes away a lot of the the photometric reliability, but you can use where the object is now you know where it is. So now you re-extract the raw counts using a polygon region in DS9, and then run the Spec Extract tool to make, remember I talked about the spectrum file, the PHA file, and the 2 calibration files, the RF and the RMF. Spec Extract will make those for you. You can load them into the Sherpa tool, run a couple basic commands, and get this bottom left picture, which is the spectral data for that cluster. And then you pick a physical model. Here I've picked the APEC model, which is a model of X-ray plasma, multiplied by an absorption model due to the foreground absorption of gas in our galaxy. I've added in a Gaussian line for fun, and then fit it and plotted the red line, which is the best fit, and the residuals. And then I ran a thing called regproj to do the same thing for many, many values of the parameters and map out the chi-squared space as a function of the temperature parameter and the abundance parameter for these physical models. And that lets me see, oh yeah, okay, I can't say much about the abundance, it's not well constrained, but the temperature is clearly somewhere around 3 kiloelectron volts. Publish. And so that gives you, I hope, a feel of how an X-ray data analysis session goes. So to summarize, we have very high spatial resolution with Chandra. No other telescope can give you such sharp pictures in the X-ray. We see a lot of quasars wherever we look. We can study supernova remnants. We can study galaxies. We can study clusters of galaxies and the hot interstellar medium. We can see these wonderful X-ray jets. And then for the analysis, our telescopes drift while observing, so you have to be always keeping in mind the difference between the instrumental pixels and the software pixels on the sky. Statistics are important. If your source only has 3 photons, you better really understand the background and the statistics to claim that that's a detection. Instrumental properties vary with off-axis angle and energy and with what day of the year it is. And we have to do this forward-folding spectral fitting approach. But we've got really good calibrated data in the archives. It's all free. It's all easy to download. It all has the same data formats. So the learning curve is not too bad. There's good science to be done. And if you use the source catalog to start with, you can get used to what the sources are like. So with that, I'll stop, and I'm happy to take any questions. And hopefully some of you are still alive.
Yeah. Thanks for such a lovely talk. Very comprehensive, very well. And as a word of encouragement, I'd like to tell people that I mean, when I visited CFA in 2015, in a month's time, it was possible to actually make a catalog. We studied NGC 281 at the star forming region, and with Scott Walk, we actually did a catalog within a month's time. And I think the Chow, the help pages, etc., everything are excellent. They're really, really very nice. I was essentially an IRAF user, but the convenience which is there with Chow is really great. And I think I would encourage others also that you can actually hit on it really nicely. It's very comfortable. It's really very nice, Chow.
Yeah.
I would say it's far more easier than IRAF or APES or the other.
Let me see if I can find. There's one web page that I want to find. Let's see if I can find it. Here we go. I'm gonna share another. If I can have just one more minute, I'll share this web page, which is let's see, where can I find this? Here we are. And share. So this, if you can see it, hopefully, is the Chow Workshops webpage at cxc.cfa.harvard.edu/chow/workshop. And this has an exercise workbook that you can work through. And it also has, if you click on previous Chow workshops and go to either of the recent ones, it has archived PDFs of presentations that go into much more detail. The first one of these presentations will look very familiar to you after my talk, but the rest of these are all, go into much more detail. And so in addition to the help pages that Priya's familiar with, these workshop talks and the exercise workbook are a good sort of in to learning how to use the system.
Yeah, great. So I'll actually propose that as some of the projects, because I don't know whether I mentioned it to you, but the purpose is after the talks, we then list projects which students can, work on for the next 3 months till we meet next.
So I think that'd be a good source of projects for you.
Yeah, thanks. So that'll be good. I'll do that. And here, questions. What is forward folding?
Okay, forward folding is the fact that we guess the spectrum, convolve it with the instrument, and predict the data, instead of the more simple way, which is take the data, divide by the sensitivity, and think that you've got the spectrum.
Okay.
So it's going in the forward direction from astronomical source to predicted data, rather than the backwards direction from observed data to source.
Okay. Thanks. And so you can unmute yourself if you want to ask questions, or you could ask in the chat window, participants. Yeah. So do we have any questions? Are there any questions? Sorry, Jonathan, you should be the one who's sleepy, not the others. Yeah. Sorry, I think when we actually get them to, thanks for an amazing talk. And I think the questions will come when they actually go on to working out that workshop business.
Yeah, I mean, this is the problem with software talks, right? Is if you're not actually using the software, it's hard to get a feel of it. So what my hope is that when you actually use the software, you will come across some of these things, and a vague memory will go, oh yeah, I remember Jonathan talked about that. I need to be careful here. And then you can go back to the presentation, which will be online, and see what I said. So hopefully it gives you that initial basis, and it gets more familiar when you do it. But it's one of the great things about archives, right, is the fact that everyone in the world can use this data. It's all public after a year. And here's the, so
and it's of the best quality.
Anka asked me, why is Chandra covering only 1% of the sky? So there are two kinds of telescopes in astronomy. Survey telescopes that have big fields of view and are searching for new things that we haven't been discovered. And what I think of as scalpel telescopes that have a narrow field of view, and they look at the things we already know is there, but they look at them in detail. So Chandra's the scalpel. So there was an earlier telescope called ROSAT that surveyed the whole sky, but had very blurry vision, right? And so it found targets for Chandra to follow up. And so Chandra, it has really high resolution, right? But that means that it doesn't cover a lot of sky. Hubble's the same, by the way. Hubble's probably less than 1% of the sky. It's just because, you're going to need another 60 years of observations to cover the rest of the sky. And Chandra's probably not going to last that long. So there's a new telescope up called eROSITA, joint German-Russian telescope, that is starting to do an all-sky survey. It's not as sharp imaging as Chandra, but it's better than ROSAT, and so that will be a really important archive to have. But the data won't be as good as, for the areas which Chandra has seen, the data won't be as good.
Great. Yeah, and the other thing in support of archival data, that it's data of the best quality. So it is exactly what people should go in for. Right?
Yeah, absolutely.
Yeah. So are there any more questions? I think everybody enjoyed the talk a lot, and we'll see what are the questions when they work it out
You can send me some by
through the
email
next
if
3-4
people,
months.
come up.
Good morning, sir. I have a question.
Yeah.
Besides instrumental
Thanks a lot.
background,
Yeah.
is there any sky background kind of thing in X-ray data?
Can you? So I didn't quite hear the question.
The question was that is there a sky background in X-ray? What is the sky background in X-ray?
Yes. We believe, well, this was a big science question. The X-ray background was discovered way back in 1962 in the very first X-ray sounding rocket that helped get Riccardo Giacconi his Nobel Prize eventually. And for a long time, we didn't know what it was. We thought it might be a diffuse background like the cosmic microwave background, but Chandra discovered the answer, which is that actually it's a lot of quasars that are so far away that they all blur together. And so if you have a good enough telescope, you resolve out the X-ray background. We've done 80% of it. There's 20% still to go, but we're confident that it's still more and more quasars farther and farther away. And so that's the bulk of the X-ray background. In the harder bands, there's a second X-ray background in soft band, which is charge exchange process, an atomic physics process of gas in our solar system. And so there's a glow from gas in our solar system where the solar wind is hitting stuff and glowing, and I don't understand the physics actually, but it's a complicated thing, and that gets brighter and fainter depending on like your sun angle and where you are in the solar system. So if you could get outside the solar system, you might be able to reduce that background. And so there's also another soft X-ray background, which is due to the hot gas in the interstellar medium near the sun. So about 1 million years ago, there was a supernova not far from the sun, and there's a huge bubble where there isn't the normal, nice, neutral interstellar medium. There's this horrible, hot, 1 million degree interstellar medium that's very thin, but glowing in X-rays. And we're right in the middle of it, right? We're sitting in the middle of this big bubble, supernova remnant bubble. And so everywhere you look, it's glowing in soft X-rays. So that's another contribution to the X-ray background.
Thanks. Thank you.
Excuse me, I have a question.
Now they're warming up.
Good.
Good morning. A wonderful talk. I was just curious, since the energy band is so large, or the energy range, why couldn't we use filters in narrower energy band regions, like in optical?
Yeah, well, but the thing is, you can write in software because we record the instrumental energy of every incoming X-ray. And so the way to do a filter with Chandra is that command line I showed you, where you just put on the end of the file square brackets energy equals 1000:2000, and you've applied you've done the equivalent of putting a color filter on the front of your telescope, but you've done it in software.
Okay, so that's in the processing we do it.
Yeah, exactly. On the fly, as an analyst, you go, I want to make these filters. And since you have a list of the energy of every photon, you can just throw away the ones that are outside the quote filter that you want to apply.
I would say that's the advantage of lesser number of photons, where you can tag every photon. Right?
That's right. Every photon
optical,
has a name.
we can't do that. Yeah. So in optical, we can't do that. But the advantage of lesser photons is each one has its name, like you said.
Yeah. There are some UV detectors that are photon counting as well that do it this way.
Thank you.
Yes. Any more questions? Jonathan is a great source to understand stuff. So if there's so I don't see any questions or so let's thank Jonathan and wish him a good night's sleep now. Thanks so much. Thanks so much for staying up for us. That's really nice, and that's been really nice of you.
So greetings to everybody. Have a great adventure in your astronomy data analysis course, and hope you enjoy the rest of the talks.
This is supposed to be a warp drive.
Yeah, well, okay. Warp factor 2 and on to Priya.
Yeah. Okay. So thanks a lot, Jonathan. Thank you. And good night to you. Bye-bye. See you. Bye. Yeah, we'll proceed now with the next talk, which is mine. But